So hi everyone, thanks for coming both in person and on Zoom. So today we have a great pleasure of having Badr-Eddine, who is going to present his work on robust estimation via maximum mean discrepancy. And for people on Zoom, you should be able to post on the chat if you have any questions, and we have a chat open, so we're able to read it. Thank you.
Great. Thank you, Antonin, for the very nice introduction and for the invitation. So thanks everyone for being here. So today I'm going to talk about some some work dealing with robust statistics using the maximum mean discrepancy. So this talk, is based on a joint work with Pierre Alquier, so who is my former PhD advisor, and who is currently a researcher at RIKEN AIP in Tokyo. So the work, the talk is mainly based on this work that has been just published in Berkeley. So first, don't hesitate to interrupt me if you have any question or something like that, so on Zoom or in person. So today I will try really to talk about the main ideas of the work. So I will try to detail a bit the proofs, which are not that complicated, just to say, but to show where all the ideas, concepts come from. So I will not focus too much on the application, on the applied part. So first, I will try to motivate a bit the work and to introduce properly what are the concepts we will handle. So the notion of robustness, of universality of a statistical procedure, what are the challenges, then how it is possible to tackle this challenge using the maximum mean discrepancy. So I will define it, what are the main properties that you can get. And finally, I will focus on a dependent setting where you have some dependence in the data. So actually, we will, in a way, we will relax the i.i.d assumption, the independent assumption of the data. So once again, don't hesitate to interrupt me if you have any question. So first, so to set up the framework, the statistical setting, so we will adopt a very classical statistical setting. So we observe a collection of random variables, so the data points that are independent. So for the moment they are independent. So and they all come from the same probability distribution. So P naught here is the data generation process. So we adopt a statistical approach. So we consider a model, okay, which is a family of distribution. And we assume that the data generation process belongs to the model. Okay, so for the moment, to make this assumption, so there exists a parameter theta naught such that P naught, the data generation process, is equal to P theta naught. So the data generation process belongs to the model, and the goal is to estimate the data generation process P naught using an estimator, so which is here. A measurable function of the data. So there is some randomness here that comes from the draw of the data and the hat over the theta hat over the theta, sorry, makes the dependence, the randomness of the estimator explicit. And what we want to do is to be able to estimate the data generating process. So what we want to have is that as the sample size grows, we want to be able to recover the data generation process, so P naught or P theta naught, given that P naught belongs to the model. So here there are 2 points of interest. The first one is we are talking about convergence, so we are implicitly, even explicitly referring to some distance. So here we are handling probability distribution. So how do we define the closeness? So we need to define some proper distance between probability distributions. And the second point is that P theta hat, so the estimated distribution, is a random quantity, given that it depends on the data. So we need to define the random notion of convergence. So either the convergence in probability, or surely in mean, in distribution, and so on. So for instance, formally, it can be defined like that. So we want that given some suitable distance between probability distribution, the distance between P theta hat and P naught, to go to 0 in mean. So we can consider different notions of convergence, but let's say that in expectation with respect to the data, we want the distance between P theta hat and P naught to go to 0, and the rate of convergence is exactly the rate at which this distance goes to 0 in expectation. So this is what in general people, it's one problem of interest in statistics. So a very classical estimator to do so is a maximum likelihood estimator. So I think that most of you are familiar with this one. So assume that we have some density with respect to some reference measure. In this case, we're able to define the likelihood. Given the likelihood, if we maximize it, we have the maximum likelihood estimator. So it's something that is very popular. And in general, when the data generating process belongs to the model and under suitable regularity condition, you have the consistency of your estimator, which means that, for instance, if you consider a Gaussian, a model of univariate Gaussians, and so the data generating process is some Gaussian centered at theta naught, then the maximum likelihood estimator in this context is just the empirical mean. And if we consider the KL divergence between distributions, then we'll get the consistency to 0 in the sense that in expectation, if we consider the KL divergence, we have the convergence to 0 at rate 1 divided by n. So this is the kind of standard results that we can have. But what we will focus on today is the case where we do not necessarily have such regularity conditions, or where the data generation process does not belong to the model. And the question is, what do we have in general? And the point is that maximum likelihood estimators, and more generally estimators based on the likelihood, often fail in such situations. So to motivate the talk a little bit, I will just present a very short example, a very quick example, a simple one, in which the maximum likelihood estimator failed. Just consider a translation. Yeah, sorry, I'm sorry. Consider a very simple translation model like that, defined like that, using this density, so on the real line. If we consider the likelihood, we see that there are multiple parameters that maximize the likelihood. So every data point actually maximizes the likelihood, and consequently, the maximum likelihood estimator is not even defined. And more generally, actually, there are situations where the likelihood is not necessarily computable, or at least maybe up to a normalizing constant or something like that. There is also another problem that can arise is that actually, I mean, when you are talking about a likelihood and a density, it refers to some reference measure. And I mean, if you consider the same distribution, for instance, a Gaussian distribution, but you consider its density with respect to different reference measures, this can result in different densities. For instance, so this was the density or the likelihood when we consider as a reference measure the classical Lebesgue measure. But if you consider another one, I don't know, for instance, the standard Gaussian distribution, then the density would be a different one. And this may result in a different likelihood, a different maximum likelihood estimator, and consequently, you may have two different likelihood estimators from the same model, the same data generating process, that would possibly have different properties. So one may be consistent, another one that may not be consistent. So there is a problem here that we see of universality, in the sense that the maximum likelihood estimator is not always defined. Even if it can be defined, it may have not universal properties, such as, I mean, depending on the reference measure, you can have different estimators that can have different properties. So this is a general point to say that we are looking for an estimation procedure that is universal in the sense that it is always defined with clear and nice property. Right, so typically the previous consistency property. Another short example of failure of the standard likelihood methods is, so we consider the Hilbert contamination model. What is this? Actually, we assume that we are interested in one distribution. So here, P theta naught. So P theta naught is in the model. So theta naught is a parameter. And actually, there is some mistake in the sense that the data are not all generated according to P theta naught, but there is a small ratio of the data that are generated according to another distribution, let us say a distribution Q. Okay, in this sense, it is possible to formulate the data generating process like that as a mixture, a weighted mixture of the distribution of interest P theta naught and of the contaminating distribution Q. And in this particular setting, so you can either want to estimate the data generating process itself, so P naught, or the distribution of interest, which is P theta naught. So a small illustration here, you see that all the dark points are generated according to a distribution of interest, so maybe a Gaussian distribution or uniform over the sphere, and you have red points that are, you see that they have a different distribution. And it may even be that all the outliers are not generated according to a fixed distribution, but that they can be anything. Actually, it's more even general than the single contamination model, in which all the outliers have the same generating distribution. And in such a case, for instance, we can see that, great, if you assume, for instance, a uniform model, and that the distribution of interest is a uniform as well, with, let's say, the parameter theta naught, which is equal to 1, if you consider the likelihood using this model, what you will get in the end is a maximum likelihood estimator, which is equal to the maximum of the data. And it is quite easy to see that if there is some contamination, imagine that, for instance, the contamination distribution Q is a Gaussian centered at 100, which is very far away from the interval 0, 1. It is quite easy to see that the maximum likelihood estimator here would be very far away from the truth, the data generating process P naught, but also very far away from the parameter of interest, the distribution of interest P theta naught, which is the uniform over 0, 1. And even, yeah. In the previous slide, yes. But in this one, not really. The real data generating process, the true one, is this one. So a mixture of a distribution of interest. Exactly. Exactly. In this precise setting, the truth, the data generating process does not belong to the model. There is some corruption here, corruption level. Exactly. And in this case, you may have two things that you want to do. Either you want to estimate the truth, P naught, or you may want to focus on P theta naught. So to consider the distance between P theta hat and P theta naught. But in this case, it is quite easy to see, for instance, if you consider the Hellinger distance, that neither P naught nor P theta naught can be estimated using P theta hat, because the distance, as in the Hellinger distance in expectation between P theta hat and P naught and P theta hat and P theta naught, or both do not go to 0. So you can see that in such misspecified setting, considering outliers, the maximum likelihood estimator is not good enough. So these are two general examples of situations where the likelihood estimator fails. Yeah. Yeah. Well, to be honest, it's not really clear. I mean, in this case, it is clear that it is a mixture. But in the case where the outliers do not have a precise distribution, I mean, it is possible that all the outliers, I mean, they may be generated not following any precise distribution. And actually, in the worst case, they can even be chosen so that they depend on all the remaining data, all the good data. So, I mean, you can have an adversarial setting where, so I agree that there can be precise situations where you have an explicit mixture. But in general, you cannot say that. The fact of modeling outliers does not always imply a data generating process that can be written as a mixture. It was just, yeah. Jonas?
So just to add on that,
yes.
I like to show these examples where and exceeding its own severity. That's something like this. I would take an increase. It's really difficult because almost every observation I'm going to just take a space where it's still
Yeah, definitely. Definitely. The higher dimensional case is very tricky in the case of outliers. So this is just to motivate a bit the search for other estimators. So what we're looking for today is a universal procedure in the sense that it is always defined. It does not depend on the data generating process nor on the model, or I mean, the existence of this estimator, and which is such that when the data generation process belongs to the model, it is statistically consistent in the sense I precised previously. So ideally, this quantity goes to 0 at a fast rate, ideally. And in case of misspecification, so if the data generating process is very far away from the model, this will not always be, it's not always possible to get these quantities goes to 0. But what we ideally want to have is to split, actually, to be able to split this distance in two parts. So the first part that in a way takes into account the difficulty of the problem, that models the distance given some suitable distribution between the model and the data generating process. So this is the distance between the data generating process and the model. And the second part that that is exactly the term that you would obtain in case of well specification. And so in particular, if you take the Huber contamination model, for instance, so the case where the data generating process does not belong to the model and can be written as a mixture, actually what we expect is that what you see is that if the ratio of outliers epsilon is equal to 0, then you're not misspecified in the sense that the data generating process belongs to the model. So what you expect is that this quantity is equal to 0, right? So what you want is that this distance between the data generating process and the model goes to 0 as the ratio of outliers go to 0. This is something that you, yeah. Yeah, yes, yeah, this is not specific to this situation. I just wanted to illustrate what we expect from this term in the case, for instance. Yeah.
So what I mean is, let's say theta is the set of theta on an interval, right? And the other is theta. The problem with the case that you restrict yourself to a reasonable input perspective. But then data actually comes from a business feature. So you have a very clear case of a specific support. Yeah, they seem to say that essentially the first term is what you have. That's fine. The second one is the approximation term. The chance that this goes to 0 fast enough, you don't have to put back that to really multiplication work is not so understood.
Well, this is another point. In your case, the misspecification is not only induced by the outliers part, right? Or no outliers at all. Okay. Yeah. Yeah.
It's completely pathological class. In that case, let's still hope that these.
We hope so, yeah. I hope so. No? This is just a general property I would like to have. So basically, if the misspecification level comes not from outliers, for instance, which can be a possibility, that comes from the choice of the support, the parameter set. I mean, this will take into account the misspecification level between coming from the parameter space. So yes, in this way, this will take this difference into account.
When you write that it goes to 0, it's really just for the example.
This with epsilon? Yeah, of course.
Yeah. It's like in there, or you just have this term.
Yeah, exactly. So this is really in this case. Yeah, Jonas?
So I don't know if I should think about what you said. Just become the different next. So basically, what's
And yeah, so just the last remark. So in this case, we have a ratio when the ratio of outliers goes to 0, we expect this quantity to go to 0 as well. So assume that this is the same model, the same parameter space. And this is something, for instance, that is not necessarily true if the distance is not well chosen. For instance, just assume that you're considering the KL divergence between probability solutions. Imagine that P theta is the set of Gaussian, so within bounded parameter space, and that the contamination distribution is a Dirac somewhere, so at a billion, very far away from this. It is, once again, as epsilon goes to 0, you expect the data junction process to go to go into the model, I mean, to get closer and closer to the model. But when you're looking at the distance, you have a distribution which is not absolutely continuous with respect to the other one. So definitely the KL divergence, whatever the value of epsilon, will remain infinite. So in a way, this quantity, in the case I mentioned, of a Gaussian, of a Dirac, and of a KL, this quantity will definitely not go to 0 as the epsilon goes to 0 as well. So the choice of the KL is quite important to be able to handle this in general, right? Just motivation for this. And so last point, so the MLE does not satisfy these requirements, of course. And there exists in the literature some estimators that satisfy this. So very shortly, for instance, there is the Yatrakov skeleton estimate that dates back to 1985, I think, from his very nice and very short paper, just 4 or 5 pages long, something like that, which just proposes an estimate that is exactly follows the scheme of the previous slide. I mean, it exactly has the properties we're looking for. So with the misspecification level here, so P standard here is not just the minimum, but everything is measured in total variation distance. Here, so we have the rate of convergence and the dimension here of the parameter space is measured in covering entropy. So this relies on having the bounded parameter space. So we have this very nice estimator. We have other estimators. For instance, more recently, there is a work by Badr-Eddine and Chérief-Abdellatif, which relies on the Hellinger distance in order to get such properties. But the problem of this estimator is that it's mainly theoretical estimators in the sense that they're not tractable in practice. For instance, the work of Yatrakov explicitly relies on the discretization of the bounded parameter space, which is quite complicated. Yeah. Doesn't, sorry? Yeah. Yeah, it doesn't depend. I mean, the first term was not supposed to go to 0 with the sample size. Yeah, this one, you mean, this one was not supposed to go to 0 with n. in case of contamination, when the proportion of outliers goes to 0, we expect this to go to 0 with the ratio, the number of outliers, but not with. I mean, it doesn't depend on the sample size at all. Yeah. Okay. Maybe. Yeah. No, here I just. Yeah. 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 I just said in general. I'm not focusing at all.
But exactly 0.
Yeah. 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 Exactly. Exactly. And yeah. Actually, you have the same kind of properties, but in having the distance. So it is based on the like tests using the boundary difference functions. It's a bit. The paper is to be honest, the paper is it's not complicated because it's very well written, but the paper is a bit technical. Yeah. 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 It's fun. Yeah. So they cannot be completed in practice, so we add another requirement. We want our estimator to be computable, right? Okay, so now I introduced the estimator we will consider. So we will use the maximum mean discrepancy, which is based on kernel methods. So just a few reminders on the kernel. So if we define, we consider a Hilbert space H and a feature map phi. So we have the same feature space as in the following. So X, the space where live the data points. A feature map is just a map, sorry, from the feature space X to the Hilbert space H. And if you define this, this exactly defines a positive definite kernel. And conversely, actually, if you have a positive definite kernel, then you will have the existence of the Hilbert space and the feature map satisfying this relation. So it's just to say that there is a correspondence between having positive definite kernel and having a pair Hilbert space feature map. And actually, it's widely used in statistics and machine learning due to the fact that quite often it's more convenient to work in the Hilbert space rather than the feature space. And so you have this correspondence, and you can, at least in theory, think in the Hilbert space. So here we will consider a positive definite kernel as well, which is bounded, assumed to be bounded. So, so we can assume without loss of generality that the bound is equal to 1, right? And actually, the same way we defined a feature map from the feature space to the Hilbert space, we will define a map from the space of probability distribution of the feature space to the Hilbert space, right? So we call this map the kernel mean embedding, and what does it consist in? So we take a distribution P or Q that is defined over the feature space, and we embed it. We have an embedding of this distribution into the Hilbert space. So it's the same thing. Instead of thinking in the space of probability distributions, we are able to think in the Hilbert space. So to see the distribution as functions via their embeddings, right? And we consider what we call a characteristic kernel. So we not spend too much time on it, but the idea of a characteristic kernel, I mean, a characteristic kernels mean that this kernel embedding is injective. What does it mean? It means that if you have two different probability distributions, then the kernel embeddings are different, right? So standard, most standard kernels or characteristics, such as the Gaussian one, for instance. And now we are able to define what we call the maximum mean discrepancy. Actually, the way to define the distance between a distribution P and a distribution Q, it's very simple. You just take the embeddings of P and of Q in the Hilbert space, and given that you have a Hilbert space, then you have a metric in the Hilbert space, and you just consider the distance in the Hilbert space between the embedding of P and the embedding of Q. So you just embed them both in the Hilbert space and consider the distance in it. And this is important to have a characteristic kernel because it means that two different distributions do not have a distance between them which is equal to 0. Just to get this. So now we have defined a maximum mean discrepancy, and we'll use it, this discrepancy, this distance, to define our estimator and to formulate the inequality, the oracle inequality we formulated previously, right? So to define the MMD estimator, it's quite easy. So what we target is the data generation process. So it would be good in MMD distance to consider the distribution in the model that is the closest to the data generation process. Given that we do not have access to the unknown data generation process, we replace the data generation process by the empirical distribution. So we use the data to construct, to build the empirical distribution, and then we consider the distribution in the model, which is the closest to the empirical distribution, right? So this defines the maximum mean discrepancy estimator. So this is the general idea of considering minimum distance estimators, so which minimize the distance to the data generating, to the empirical distribution, sorry. So it's a very long idea, a very old idea. And there has been in the 70s the idea that choosing wisely the metric in this minimum distance estimator would lead to robustness. So we use this idea in the context of using the maximum mean discrepancy. So this idea actually has been proposed a few years ago, so in 2015, using in generative adversarial networks. But the first theoretical study dates back to a paper written by FX and others that was so not yet published, but that appeared on the archive a few months before our paper. So this is the first theoretical study that provides a few asymptotic results and as well as some results that we cover in this work. Right?
You estimated like
You mean this part itself? Is it a biased one? Non-asymptotically, you mean? Maybe, yeah. So I mean, it's not the focus on the.
There's no proof of unbiased.
Yeah. Yeah. Let's say this. Well. So, and just a last word. So I will not really focus on this part in this talk, but just to say that really one of the main motivations of using the maximum discrepancy is that this estimator is quite convenient to work with because it is quite easily tractable, actually. So using the formulation in the reverse case and the fact that the feature map in this case can be written explicitly using the kernel, the MMD distance between distribution p theta in the model and p hat can be written like that. Okay. And the point is that even if the model does not have any, even if you do not have an explicit density that you can evaluate or something like that, as soon as you can sample from the distributions in the model, this is quite easy to approximate this objective and actually to approximate it using, for instance, Monte Carlo approximations, right? Yeah. 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 Yeah, so typically you can minimize, try to minimize this objective using, for instance, a stochastic gradient descent, given that you are allowed to sample from the distribution in the model. So for instance, if you have a density, you have an explicit formula for the gradient, and you can, so once again, you can approximate it using the Monte Carlo approximations. And so just to say that as soon as you can sample from your model, right, it is quite easy to, in practice, optimize this objective just by performing stochastic gradients. So this is the main idea why this estimator is quite convenient to work with, right? I mean, it could depend on the kernel, but it's not always that easy, to be honest.
it's when you take the gradient.
Yeah.
Like how do they work for the first term?
This one? This one?
Yeah.
It just cancels.
It's just you.
Yeah, yes. It doesn't depend on theta. The only dependence on theta is on the expectations. So really, you just have to. Here, you just have.
Yeah, the excited.
Yeah.
That end data.
Yeah, exactly. Exactly.
And this is actually the video of the example or the one sample. Yeah, it's what I guess if you want the main entire it's one of those.
Crazy. So let's skip this part. So the main result. Yeah. Oh, sorry. Yeah. Okay. So actually, in this, so you mean in this formula? So yeah, explicitly in this formula, I say that if we have some density, you have this formula. But even if you do not have a density, this will hold. And I mean, as soon as you are able, depending on theta, I mean, assume that in order to sample from p theta, you have a transformation of a Bayes distribution from which you can sample. You can still compute the gradient of this, even without considering the density. But so just imagine that p theta is a forward of the Bayes distribution. So it depends on theta, you can have some for instance, like that. So this is, I agree, this is valid when you have a density, so in order to be written in a quite convenient way, but it's not something that you need. Right? Great. So the main result, the main results of the paper is one of the main results is that this formulation. So you're seeing the i.i.d setting. We have a model that does not necessarily contain the full data generating process. So we have exactly this property, which is exactly the same as the general formulation, previous formulation. So the distance between the p theta and the p naught is bounded by. So this is the misspecification level. So the distance in MMD between the model and the data generation process plus the rate of convergence. So just one word on that one. Very shortly, the question is, if you consider here this rate of convergence, is it possible to achieve a better one? So in general, the question, the answer is no. If you, for instance, achieve a major process model, you cannot make any distance. If you do not make any additional assumption on the model, it is not possible to get this. So this is the first remark I wanted to make, and the second one is that it is also possible to get a result instead of expectation with high probability. So the only difference is that simulation term here, which depends on the confidence level. So this is quite so in this case, I will show the proof, which is very simple. In this case, we apply geometry. Yeah. 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 So this is a question. The choice of the channel. I mean, if you optimize the right hand side. Yeah. 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 So this is not true, for example. Oh yeah, not making an assumption on so No. I'm sorry, there is a lag, so.
So whenever you do
In the end, when you have, although, I mean, and what you want to estimate in the end, for instance, the distance between the hat and theta naught and the theta naught, you know what would be the optimal rate of the button, for instance. So you know in theory what would be the optimal. I mean, if you just want to tune, for instance, gamma, you know from the bound what would be the optimal gamma. You know what I mean? So changing. No, not all. Wait, yeah. Yeah. Yeah.
You just say zero is more. Yeah, you could take the infinite. Or like something.
Should I go or yeah. Yeah, so the proof. It's just to say that to show that the proof is very simple. Actually, you can prove this in two steps. The first one, consistency. So instead of thinking in expectation, let's think about three to begin with. So this distance between theta hat and T naught, we use the triangle inequality by incorporating T hat. So this is bounded by this plus this. Triangle inequality by basic, right? The second stage is to notice that this, by definition, the minimizer. I mean, this is definition of the theta MMD. So whatever the value of theta, this is smaller than this by definition of the MMD estimator, right? So you get this is the boundary by this plus this. Given that what you are interested in here is not to have a not, you once again use triangle inequality here. So this is bounded by if you have not plus not, which is that the same as here. So very easily from the definition of the estimator, I'm using triangle inequality, we have this inequality. This holds for any value of theta, so we can take the infinite of theta to give that this is emotionally bounded by this plus 2 times this. So the only thing that is that we need to do now is to show that the expectation, this quantity here, is bounded by 1 divided by the square root of them. Okay, so the quantity really is the quantity of interest. You want to control this expectation, right? And as you can guess, if you want the result with high probability, you just need to control this with high probability, right? And to control this, it's not that difficult. The second stage is that, so we think we take the square. So we use Jensen to make it the expectation. Then we write the MMD distance using the Hilbert space notation, right? The Hilbert space distance. Actually, we just noticed that all these quantities always, so this is centered and these kernel embeddings are independent, given that the data points are independent. So here you have, so here this is an assumption. So you would have like cross terms, expectations, and what you just need to notice is that you can see this expectation as a variance term, but expressed in the Hilbert space, right? So this is bounded by the second order one of the kernel embedding of delta x1, which means that given that we are in the Hilbert space, the kernel is bounded, everything is bounded by 1. So this quantity in the expectation is bounded by 1, and the only thing that is left is 1 divided by 2. So this is done. Yeah.
Can you why you say the big point in like a small root?
From here to here?
Yeah.
Actually, you just develop and use so you get so like dot products between xi, function of xi and function of xj, and the expectation this is equal to 0. So if you develop
all the constant.
yeah, exactly. So this is just the 0 right here. And given that kernel is bounded, you have this. So and it's possible to control this with majority input. So this is just the proof. I just wanted to tackle as well the contamination setting. So in the contamination setting, once again, you can either want to target the data going to process P0 or the distribution of interest P theta naught. So if you want to target P0, that's all. If you want to target P theta naught, given the triangle inequality, you're done if you're able to control the distance between P theta hat and P0 and the distance between P0 and P theta naught. So the only thing that you have to do is to control the distance between P0 and P theta naught in the Hilbert contamination model, for instance. And actually, so I wrote the Hilbert contamination model, but even in the adversarial setting, you can still show this. So not using this proof, but you can still show this. It's very easy to see. So this, write this in the Hilbert space. Then you rearrange the terms using the epsilon, and then you use the triangle inequality. So in the Hilbert space, okay. So you get this, and given that the kernel is bounded, this gives like 2 times epsilon. So actually, this quantity, this infimum here, is indeed a quantity that goes to 0 with epsilon at rate epsilon. And what you finally get in the case of Hilbert contamination model, is it possible to control the distance between P theta and P0? And this is split in 2 terms: the terms that only depend on epsilon and the terms that only depend on the sample size, right? So it is something that is very convenient and satisfies what I told in the beginning, what we expect in the Hilbert contamination model. So a very short example. So if we are considering Gaussian distributions, a Gaussian model, and we use a Gaussian kernel, so we have an explicit formula for the energy distance between Gaussians, and what we obtain in the end is this rate of convergence, so which is split in two terms, the dependence on the ratio of outliers and the dependence on the sample size, right? So we only have this, and this is optimal in the minimax sense, which means that you cannot do better in the worst case. So I just have to mention that it is true that in high dimension, this is not true anymore, but I will not delve too much into detail for that. We can discuss later, maybe. Yeah. It's in like I take the square, so you can just take. I mean, if you have a square root, you do not have a square.
Yeah.
Right. But this is generally what you have. And a very small. This is really a toy example. There are more sophisticated applications in many papers, but basically, if you consider so the standard case, which is well specified, the MMD and the MMD estimator are comparable. If you have 2% of the observation that are not drawn from the true Gaussian distribution, but from the Cauchy, you can see that MMD is much better. And if you only take 1% of the observation, so even less outliers, but with a worse outlier in the sense that the outlier is very far away, you see that the MMD completely fails, which is not the case of MMD estimator. Yes? Yeah.
You're actually something different than what you have from
yeah, it's yeah. Theta hat and theta naught. Yeah. We have a contamination model. It's exactly it's exactly this setting. Yeah, it's exactly this setting, but just we computed the mean absolute error instead of the square error.
Yeah, so you get back to your score plus whatever.
Even before this one? Yeah.
Yeah. It's clear that infection is large than the standard factors. Fail. And if you want to assess how much you fail, you have to
well, let's take a particular case, which is just the next slide, right? Actually, what you have this rate of convergence in dimension 1, I mean, is minimax optimal. So in epsilon and in up to a constant of it. Yeah, it is what I'm saying. So this is not true anymore in high dimension, because in high dimension the optimal rate would be with a d over the n, and we get a d as well here. But I mean, you have a case where this is optimal. So basically, the lower bound is this one. And so that's all I wanted to show for this part. Yeah. Which kernel, sorry? I'm not sure I see what kernel it is, but yeah, we only apply it to bounded kernel. So I cannot answer your question. Sorry. And so very shortly for the last part, because we run out of time. I mean, I try to be very short. So the question is just what about the case of dependent data, right? If there is some dependence in the data set. So the question actually, most consistency results are based on a more simple result. So either can be the central limit theorem, the law of Legendre, deviation inequality, and so on. So the question is not does our main general result, our final result hold in the case of dependent data, but it's boils down to wonder whether the most basic results that we use, for instance, McDermott inequality, holds in case of dependent data, right? So this boils down to asking this question. And actually, there is a huge part of the statistical community interested in the dependence setting, which tries to understand to what extent it is possible to relax this asymptotic, this independent assumption, right? So for people working on time series, what they noticed and they are studying is that in practice, actually, it is possible to still have central limit like theorems or deviation theorems. So their theorem can still hold even when the data are not independent, but almost independent in the sense that assume, for instance, a stationary process. If the series is not independent, but asymptotically independent, it means that if you consider xt and xt plus h, they are not independent, but this dependence between xt and xt plus h is vanishing as h is going to infinity, right? So the further the points in the series, the lower the dependence between them. So we say in general that a mixing stationary process is a process that is not independent, but asymptotically independent. So there are several ways to define asymptotic independence. So depending mainly on the way you measure the dependence, because something that is quite arbitrary, and the rate of decay you require for your sequence. I mean, you can say that, okay, it is true that it is vanishing, asymptotically independent, but the rate of decay of this correlation is not fast enough. So you can say that, no, my stationary process is asymptotically independent, but not fast enough in a way. So actually what we require for such mixing properties, actually we want to define a measure of dependence and a rate of decay such that actually the final goal is to get some deviation inequalities, for instance, large deviation inequalities. So if you have some definition of asymptotically independent stationary series, but even under this assumption, you do not have any theorem, it's not interesting. So what you want is to be able to have a condition that makes it possible to have some result in the end. So for instance, you want a central limit-like theorem. So you want a condition that will imply the result. The first one is that you do not want the idea is to relax the independence assumption. So if you have a condition that would imply a central limit-like theorem, but your condition is as if your data were independent, it's not really interesting. So you need to relax it enough so that many, for instance, a Markov chain can be asymptotically independent. And the final point is that this condition can be checked in practice, because if you have some condition that is very good, it is necessary and sufficient to get a central limit-like theorem, which is not requiring the independence, but you cannot verify if your series satisfies it or not. It's not very interesting. And we'll see how it is possible to do this with MMD and with a measure of dependence that satisfies the three conditions. So very shortly, what was the problem in the previous case? It was the problem of controlling this expectation and with high probability. So to go back to why it is equal, it is the point actually. If you do not have the independence assumption, you have this first term actually, which is. So basically, I told you that this can be seen as a variance in the Hilbert space. The same way, this can be seen as a covariance in the Hilbert space. So the way we measure the dependence between xt and xt plus h is just considering this covariance in the Hilbert space. So this is how we define our correlation, our dependence measure between xt and xt plus h. So we assume that the process is stationary, so that it does not depend on c, but only on h, right? And so this is what we call our dependence coefficient. And so what we have directly from what was shown previously is that this can be controlled in expectation by 1 divided by n, so what we had, plus this sum divided by n. Okay, so this is really straightforward. And so we have the following theorem, which just, I mean, we exactly have the same result as previously, just with an additional term here, which is the sum of the dependence coefficients on top of over the sample size here. So we say that our stochastic process is asymptotically independent, weakly dependent in a way, as soon as the series of this correlation coefficients is summable, right? So to explain this, if the rate of decay of the dependence correlation between coefficient between xt and xt plus h, for instance, is exponential, if it's exponentially quickly decaying in h, for instance, you will have a similarity, it's okay. If the dependence of the covariance between xt and xt plus h in the Hilbert space as 1 divided by h squared, this is okay. If it's 1 divided by h, it will not be okay because nothing like that. Just the basic idea. And actually, most conditions in the literature are formulated like that. People say, okay, we want to get a central limit Lie theorem for dependent stationary processes. And they say, okay, I define this kind of coefficient, which is different from our coefficient, but, and they say, okay, if for this coefficient, the series is summable, then we can say that we have a summability. So there are a lot of mixing coefficients like that exist. And another remark, which is, it is also possible to extend the bound with high probability, but with an additional assumption, which is kind of a dependent version of Maximum inequality, right? And just the last part, which is to show that, so I showed that I found a condition that is sufficient to show that we still have our result, but just what I will show now is that it's widely applicable. So it's applicable to a wide range of models, for instance, autoregressive models, okay? And that is very easy to compute. So it is very easy to compute. On the contrary to some like mixing coefficients, which are the most, not necessarily the most widely used, but the historical ones, which can be quite difficult to compute. And actually, if you consider an autoregressive process, so with this kind of time series, if the noise here is bounded in expectation, have a finished first order moment, then actually the rate of decay of the covariance in the Hilbert space is exponential. So it's exponentially, so given that the matrix here is has a norm lower than 1, then the dependence in H, I mean, it's this time series is asymptotically independent with a rate of decay which is exponential in H. So this is summable, and this will satisfy the previous result, the main result that we wanted to have, even with dependent data. And the last result, a last example, actually, a very popular dependence coefficient is so what we call mixing coefficients. So in particular, the alpha and the beta one. And there is an example of process of stationary process, which is non-mixing with respect to a very popular coefficient, which is a beta one. So it is defined like that. So it is very easy to understand. How to understand this one is, so x0 is a uniform round number between 0 and 1. So assume that you uniformly have random sample one number like that, and you write its decomposition as a binary digit, so 0.101, for instance. So xt plus 1 can be obtained like that. So you just sample uniformly at random digit 0 or 1, and so you take your initial number, so 0.101. You shift the numbers after the dot to the right, and you incorporate the new one, so 0 and 1, and you do it at each step. So you have 0.101. For instance, we sample a 1. You shift everything to the right, and you have 0.1101. So x2 will be, you sample 0, 1, let's say 0, you will have 0.01101. And at each step, actually, your first x0 is 0.101 after the dot. You shift it at each step to the right, and you incorporate a random number either 0 or 1. So actually, if you know xt plus 1, you know xt. Yeah, I can, but just to say that there is a deterministic relationship between xt plus 1 and xt and xt plus h. And if you know xt plus h, you know xt, because you just keep the last digits, actually. So this is why it is not mixing in the common sense, but using our definition of mixing, it is, and with an exponentially fast decaying number. So it satisfies. And more generally, we showed that given the most common definitions of dependence, it is of mixing. It is. So I mean, as soon as standard conditions are satisfied, our condition will be satisfied as well because it is enabled. Okay. So this is the last thing I wanted to say, just to mention a few other works. So I tackled a Bayesian version of this one with my fellow PhD advisor. So just like propose a Bayesian, pseudo-Bayesian variant of it. There is a nice recent paper by Jeremias, you can see on the effects that appeared on i.i.d. So this year, based on MMD postdoctoral bootstrap. So you have the most older, GAN paper, so using the MMD in generative adversarial networks. And there are like semi-parametric estimation. So in case where you, for instance, in regression, you're quite often interested in the conditional distribution, and you do not want to specify the law of X. So in this case, you need to build estimators that are a bit different in the sense that are semi-parametric. The Pierre wrote a paper on that dealing with regression, and so we studied also a paper dealing with calculus, so there are many other papers on the topic, in particular with slightly different metrics such as the Statistical discrepancy and so on. But yeah, that's all. Thank you for your attention.